Water electrolysis is a non-spontaneous process with the Gibbs free energy change being positive under the practical temperatures and pressure conditions. However, the Gibbs free energy change, it becomes negative at temperatures about 2000 Kelvin, which are very harsh conditions to operate at. In the last class we have seen the major components of the electrolytic cell, which is the basic unit of an electrolyzer, and we have seen that it has two electrodes, an electrolyte and a diaphragm separating the two electrodes. Now these electrode and electrolyte, they have an interface depending upon the cell configuration, and at these interface the various electrochemical reactions take place. There is an external supply connected, and this is to adjust the Fermi levels of the electrodes. So, the redox couple reactions can take place. Now, in this the electrons flow through the external circuit and the ions flow internally into the electrolytic cell. There is a separator, and this separator performs two functions. One, to physically separate the two electrodes. At the same time, the product gases which are released at cathode and anode to prevent the intermixing of these gases, so that hydrogen from the cathode side can be collected and oxygen from the anode side can be collected separately. So, this is what we have done in the earlier class. These components can be connected in different possible arrangements. Basically, there are three such concepts which are there of arranging these components in an electrolytic cell. The first concept is that of a gap cell, in which there is a gap between the separator and the two electrodes. Now, this is the simplest and the most conventional type of the arrangement concept, wherein the distance between the electrode and the separator is such that the products or the gases which are formed, they are evolved, and it is low, so that the ohmic resistances across the electrolytic cell is lower. Now, in this arrangement, the major disadvantage is the products which are coming out, or the gas bubbles which are released, they form a sort of thin film onto the surface, and that is a resistive layer which is formed on the surface. Thereby it limits the current density which could be achieved in this particular configuration. The second concept is that of a zero gap cell, where the separator is pressed across the two electrodes. The electrodes here are porous with electrolyte present in the interpolar region, and this separator has a zero gap with respect to the electrodes. Now, in this particular arrangement, the ohmic losses are low compared to the gap cell, and as such high current densities can be achieved at lower voltages in this particular configuration, and this configuration is used for alkaline water electrolysis. There is a third concept which is primarily for the polymer electrolyte membrane based electrolyzers, where the separator is a membrane, and this membrane selectively allows the ions to pass through. This membrane on both of its surfaces has porous electrocatalytic layers, and then it is pressed across the current collectors. Now, in this arrangement we can achieve higher current densities and higher efficiencies. So, these are the 3 possible arrangements of the various components of an electrolytic cell. Also we have seen in the last class that the minimum required voltage for the electrolysis to take place, which is V reversible, is 1.23 volt. Now in this voltage the various components of the reacting species are in the gaseous form. So water is present in the water vapor form. However, the required energy for converting into water vapor, if that also comes from the electrical energy and the process becomes isothermal. So under these conditions, when it is the cell is not taking any heat from the surroundings or it is acting in an isothermal condition, then it is known as thermoneutral voltage, and its value is 1.48 volt, which we have seen in the previous class. But under this voltage, in actual condition the process occurs at a very slow pace. This can be accelerated by applying an extra energy or an extra voltage, and this extra energy or extra voltage which is required under practical conditions, under real operating conditions, is known as over voltage. Now there are 2 reasons for existence of this over voltage. One is because of the low conductivity of water, which can be increased by adding salts, acids or bases, and it is also because of the large activation energy barrier, which is for the splitting up of water, and that can be addressed by appropriate selection of electrocatalysts. Under practical operating conditions, when the current densities are higher for higher hydrogen production, the required cell voltage lies in the range of 1.8 to 2.05 volt. Now under these conditions there are several irreversibilities involved in the cell, like there are resistances offered inside the electrolytic cell by the various components. There are resistances towards the charge transfer, towards the charge transport, and all those result into voltage drop. So these voltage drop can be across the electroactive layers present between the various electroactive species and the electrode surface. It could be because of internal resistances inside the electrodes. It can occur at the interfaces where the charge transfer occurs. It can be within the solution across the diffusion layer near the electrode surface, which is arising because of the mass transfer limitations. So in the previous class we have seen that there is a compact layer, then there is a diffuse layer. So there could be voltage drop occurring because of the mass transfer limitations. Also during the transport of ions in the bulk electrolyte, there may be an additional resistance which is offered, or within the cell separator. Now all these factors, they contribute towards voltage drop within a electrolytic cell under practical operating conditions. So under that condition, the overall cell voltage is a sum of reversible cell voltage, another term which is arising because of the ohmic resistance or losses within the cell, third term which is arising because of the activation over voltage, and the last one because of the concentration over voltage. So the total cell voltage is a sum of all these voltages. First one is a thermodynamic reversible voltage which has a value of 1.23 volt. Second one, which is an ohmic over voltage, this is arising due to the ohmic losses within the cell, which is because of the electrical resistance offered by the various components of the cell. These could be electrodes, the interconnections, current collectors, and this particular part of the voltage over voltage, this is proportional to the current flowing in the electrolytic cell, and it is having a linear nature. The third term, which is the activation over voltage, which is arising because of the electrode kinetics, this is the energy barrier which charge carrier has to overcome when it moves from the electroactive species like the reactants towards the electrodes and vice versa. So an extra energy or an extra voltage is required, that is to cross this energy barrier by the charge carriers, and this comes in the form of activation over voltage. And this activation over voltage, this has a logarithmic nature. the last component, which is the concentration over voltage, this arises because of the mass transport limitations in the electrolytic cell. Now the products which are formed, if their concentration is higher than the reactants at the interface, so the products which are formed are not removed at the pace at which so that the reactants reach the interface so that the reaction can take place. In that case there are concentration over voltages resulting. Now if we look at a typical current voltage characteristics where cell voltage is plotted against the current density, then we can see that there are 3 regions in the IV characteristic. So the first region, which is showing a logarithmic nature, this is arising because of the activation over voltage, and this activation over voltage dominates at the low current densities, and the ohmic over voltage is very less in this particular region. As such, it is logarithmic in nature, and thereafter there is a linear nature which is observed in the IV characteristic. So in this linear region, the activation over voltage potential is less dominated than the ohmic over voltage, which is offered by the electrical resistance of the various cell components. Now in this linear region, which is also proportional to the current flowing, this depends upon even the surface area, like this is much more dominating in the large area industrial scale electrolyzer. This ohmic over potential could be very high in that case. And the last region where after this linear region there is a rise, that is because of the concentration over voltage or the mass transport limitations in the cell. Now the various thermodynamic potentials that are calculated, which we have seen in the earlier class, these are calculated under equilibrium set of conditions. By equilibrium set of conditions we mean that there are no irreversibilities involved, but in actual practice the cell voltage it required is sufficiently higher because of the various irreversibilities in the cell. These are arising, as we have seen, because of the resistances of the different components, because of the activation over voltage, because of the ohmic over voltage, and this over voltage can be related with the current density using the Tafel equation. So the over voltage is given by A plus B log I, where A and B, these are characteristics of anode and cathode, and I is the current density offered. So in its terms we can write that the cell voltage is equal to the reversible cell voltage plus the over voltage, which is the activation over voltage plus the concentration over voltage plus the current flowing through the cell and the total resistance arising because of the various components of the cell. So this is how the overall cell voltage, the total cell voltage is related to the various over voltages and the thermodynamic reversible voltage. Now the kinetics of electrolysis, in the absence of any mass transport limitations, the charge transfer kinetics at the interface can be given by the Butler-Volmer equation, where the current density is given by the exchange current density times this quantity, which is exponential beta NF upon RT neta minus exponential minus of 1 minus beta NF upon RT neta, where beta is the symmetry factor, N is the number of electrons exchanged in the process, F is the Faraday's constant, R is gas constant, T is the temperature, and neta is the charge transfer over voltage. Now I naught, which is the exchange current density, which is expressed in ampere per centimeter square for the half cell reaction, this is the major kinetic parameter, and this determines the efficiency of the charge transfer process. This is an intensive property. The higher is this current density, the more reversible the reaction will be and the more efficiency of the process will be. So the best electrocatalysts are those which gives high exchange current density. Now till now we have seen the different components of electrolytic cell, and then what are the thermodynamics, what are the kinetics, what are the cell voltages involved in a single electrolytic cell. Now these hundreds of these electrolytic cell can be combined together to form a stack, electrolysis stack. Now there are different conformations in which these can be combined. Like there are the two well known combinations are unipolar or parallel arrangement of the electrolytic cell and the bipolar or series arrangement of the different electrolytic cell. There is a third combination also possible, which is a hybrid one. So, some cells are connected in series, some cells are connected in parallel. However, hybrid combination is not preferred arrangement in an electrolysis stack. Now, let us look at these combinations. The unipolar or the parallel arrangement, wherein each electrode is having a single polarity in each of the electrolytic cell. This is also known as a tank electrolyzer. So, although there are simplified connections, so as such it is simple to connect, it is robust, but it requires more of space. Since there are several connections involved, so there are more of losses involved in the arrangement, and it can also result in non-uniform current densities because the internal resistance of different cells may be different. Now, there is another arrangement where the different electrolytic cells could be connected in series. So, negative of the first connected to the positive of second and same way. So, the bipolar or series arrangement, it is also known as filter pressed arrangement. This is little complex in terms of the arrangement, however it is compact and a high current density could be obtained using this particular combination. The most widely used combination is the bipolar or the series arrangement, and in this the voltage of the stack, it depends upon how many number of cells are there in the stack, and it is number, if each of the cell has V cell voltage, then it is N cell V cell. However, the same current flows through the stack as that of the individual cell. However, here the current obtained in the unipolar or the parallel arrangement is number of cells times the current passing through the individual cell in the unipolar arrangement. So, the most widely used arrangement is that of the series combination or the bipolar arrangement. Now, when we have a stack, then the obvious question is how much amount of hydrogen we can produce using that particular electrolysis stack. So, the Faraday's laws, which relates the amount of hydrogen which can be produced based on the amount of charge being transferred, that could be given by the rate of hydrogen produced can be given using the Faraday's law as, so the hydrogen production rate, which is in terms of normal meter cube of hydrogen being produced per hour, it is given by the Faraday efficiency neta F times N cell I cell. So, if there are N cells, number of cells being connected in the stack, each of the cell is having a current flowing of I cell upon ZF, where Z is the number of electrons being transferred, 2 in this case, F is the Faraday's constant, and then there are certain quantities to convert it into normal meter cube per hour. So, this is the amount of hydrogen which can be produced using an electrolyzer. Now, the first term here, which is the neta F, this is the Faraday efficiency. This is also known as the current efficiency, and it is defined as the amount of electric charge which is required to produce a certain amount of hydrogen under the ideal conditions. So, the ideal quantity of the electric charge required to produce a certain quantity of hydrogen under ideal situation to the electric charge which is actually consumed in producing the same amount of hydrogen using an electrolyzer, and this quantity is usually less than 1. So, its value is less than 1, and the reason for this being less than 1 is as compared to the ideal situation, the amount of energy consumed is always higher in case of the actual practice. This is less than 1 because of the presence of different parasitic currents. These parasitic currents, they actually flow through the electrolytic cell, but they do not contribute towards the hydrogen production, and if they participate or they may participate in the unwanted reactions, or if at times certain amount of hydrogen is being produced, that may be lost, it could not be collected in the process. So, as such, if the electrolyzer is operating at a rated production capacity, then usually this value of the Faraday efficiency is less than 1, and typically max it can be even 0.95 or even slightly more than that. Now this Faradaic efficiency or the current efficiency, this is different for the different electrodes. The anode at which the oxygen evolution occurs or the oxygen reduction reaction occurs, this is always more demanding, or the reaction is much more slower than the hydrogen evaluation reaction which occurs at the cathode side, or the hydrogen oxidation reaction that occurs onto the cathode side. Now this can be again represented by, on the anodic side, the Faraday's constant and the rate at which the gases are evolved times the current, actual amount of current being consumed, and same it is onto the cathodic side. Now this, it is desired that the gases which are evolved in the process of electrolysis, they should not intermix, or there should not be a crossover. Like the hydrogen which is being produced onto the cathode side can go onto the anode side through the separator, membrane or diaphragm, and can either, it can combine with oxygen or it can reoxidize, and that is an undesirable phenomena, because it not only results into loss of the electrical work which we have provided so as to produce hydrogen and oxygen gases, at the same time it increases the heat dissipation into the cell, and that makes the process inefficient, reduces the efficiency, and all this crossover arises because there is a non-zero solubility of these gases, product gases, oxygen and hydrogen, which are produced in the electrolyte. At the same time, the separator which is being used, that also has a non-zero permeability, and because of this crossover it reduces the Faradaic efficiency in the electrochemical cell. Now how much amount of energy is consumed in an electrolyzer to produce a certain amount of hydrogen is given by the specific energy consumption. So the specific energy consumption, which is CE here, it is in kilowatt hour per normal meter cube of hydrogen being produced, and this is given by the amount of energy consumed to produce hydrogen divided by the amount of hydrogen being produced. So the amount of hydrogen being produced in the denominator. So this is an integral over a period of time of a product of N cell, the number of cells in the electrolysis stack, current flowing through each of the cell, and the voltage of the cell, that is being integrated over a period of time delta t, 0 to delta t, and in during the same time the amount of hydrogen being produced is there in the denominator. Now when we consider this in the electrolysis process, the specific energy consumption, however the under actual conditions there is more energy consumption because of the different auxiliary units which are there, the different auxiliary components in an electrolyzer. These could be valves, these could be sensors, these could be purification systems which are used, cooling systems which are used, and then there can be power losses involved in the process. So the actual amount of energy which is consumed is higher than the, in the case of electrolysis in the system, the global hydrogen production system. At the same time, the denominator which indicates the amount of hydrogen being produced, that also may have certain losses. So the hydrogen which is being produced may undergo losses at the different walls, at different interconnections, and all of that may not be collected at the purification system also. So if we consider all those, the added amount of energy which is required by the auxiliary components and the power losses involved in the numerator, and at the same time the various hydrogen losses are included in the denominator, then the specific energy consumption will be different from this particular formula, and then it becomes the specific energy consumption from a global hydrogen production system. Another important parameter in an electrolyzer is the efficiency of the electrolyzer. Now if it is an energy efficiency, then it is the minimum amount of energy which is required to split 1 mole of water to the actual total amount of energy required. So if it is in terms of Gibbs free energy, then the reversible cell voltage upon the actual cell voltage, or it could be in terms of the enthalpy, energy efficiency in terms of enthalpy. So this is the thermoneutral voltage divided by the cell voltage. So this is the thermodynamic voltage divided by the actual amount of energy required or the actual cell voltage. Now in ideal conditions, when we are calculating the various thermodynamic voltages, these are calculated under equilibrium conditions when the system is reversible. So under equilibrium condition, the energy required under reversible conditions is equal to the energy required under irreversible conditions, and in that case the energy efficiency of the cell becomes 1. However, the actual cell efficiency is given by the amount of energy required under reversible conditions divided by the energy required under irreversible conditions. So the denominator accounts for all the irreversibilities involved in the process. In actual practice, always the W reversible, so this is less than the W irreversible, the amount of energy required because of the irreversible processes is more. This is because of the parasitic resistance, the various resistances, electrical resistances involved, the various over voltages that requires additional energy in the process. So the energy efficiency of the cell is less than 1. It can also be represented in terms of the energy content of the products which are formed to the total amount of energy which is required to produce that product. So the products formed are here hydrogen and oxygen, and the amount of energy which is required to produce these products. This can be given by the higher heating value of hydrogen being produced. So the amount of hydrogen which is being produced, its higher heating value divided by the specific energy consumption in the process into 100. In higher heating value can be taken as 3.54 kilowatt hour per normal meter cube, but this higher heating value is taken in low temperature electrolysis process where water is electrolyzed. However, lower heating value has to be taken for high temperature electrolysis process like solid oxide electrolysis, where the water vapor is available for the electrolysis process to take place. Now if we consider all the other losses, all the additional energy requirements in the expression, then the efficiency under that conditions is known as the global hydrogen production system efficiency. So again the energy required including all the peripheral components and the losses, then it becomes the actual efficiency of the electrolyzer. To summarize this portion, we have seen the various configurations in which the different components of electrolysis unit can be connected and how these electrolysis cell can be integrated together to form an electrolyzer stack. Also we have seen the various over voltages which arises due to the ohmic losses, concentration and activation losses in the process of electrolysis. We have seen what is the efficiency of an electrolyzer and how we can improve onto the energy efficiency, and that can be done by reducing the irreversible losses like the different over voltages and the resistances involved in the process needs to be reduced. These over voltages can be reduced if we select an appropriate electrocatalytic material, especially on the anode side, because the oxygen evaluation reaction is more demanding and slower compared to the hydrogen evaluation reaction. We have also seen the kinetics of the electrolysis process, and the gaseous products which are released, they can also undergo crossovers or intermixing, and that result in loss of the electrical work. At the same time it can result into heating due to recombination, and this is more prominent under high current densities and high operating pressures arises because of this condition arises because it is non-zero solubility of these gases inside the electrolyte and non-zero permeability of the separator. In the next class we will see the different configurations, different electrolyzer technologies which are there in detail. Thank you.